Hi students, good morning. So today we will discuss about heat transfer subject which is included in the Tsgenco examination. So today I will start about heat transfer. In heat transfer, this is the 12th chapter for this examination. It is given in the syllabus. So the first topic in this heat transfer subject is they given in the syllabus modes of heat transfer. So before we going into modes of heat transfer, we should learn the basic about what is heat transfer. So that we will go into the modes of heat transfer. So what is heat transfer? Heat transfer is nothing but it is a mechanism that will happen when there is a difference between two bodies, difference in temperature between two bodies. That is called heat transfer. For example, there is one body which we can name as a body A. This is body A and this is body B. Let us take this body A at 80 degrees Celsius and body B at 60 degrees Celsius. So that what I said, that heat transfer is a mechanism that will happen when there is a temperature difference between two bodies. Suppose the A body is at 80 degrees Celsius, body B is at 60 degrees Celsius, so that the heat will transfer always from higher body to lower body, so that the heat will transfer from body A to body B. So this is called heat transfer. In this, the first topic in our syllabus is given modes of heat transfer. So in modes of heat transfer, there are three modes of heat transfer. Let me write the title, modes of heat transfer. First one is, first I will erase this. Here I will write. The first one is conduction. This is the first mode of heat transfer. Second one is convection. Third one is radiation. So these are the three modes of heat transfer: conduction, convection and radiation. Conduction is nothing but it's a mode of heat transfer that will always happens in solid bodies. Maximum solid bodies only conduction happens. For example, if you take any solid rod, so for example, let us consider this is a solid rod, or it is a steel rod which is made of steel. So this steel rod, inside this steel rod, these molecules are there. These molecules are closely packed. So these are the molecules. So the gap between the two molecules are very less. So that we can say inside this steel rod molecules are closely packed. Suppose if I heat this steel rod at one end, here I am supplying a heat. Here I am supplying a heat. If I supply a heat at one end of the steel rod, then the heat will transfer from this end to that end. So that also we already discussed the mechanism of heat transfer. So that heat will always transfer from higher temperature region to lower temperature region. So in conduction, what happening, when we heat this rod at one end, what will happen, these molecules will start vibrate. These molecules will not move from this place to another place. Instead of moving, because these all molecules are closely packed, so that it will not move. So what it will do, it will vibrate from its place, so that it will vibrate at some high amplitude. This molecule will vibrate at one amplitude, and the molecule which is above this molecule also will start vibrate when we heat it. So that when the molecule starts vibrating, due to that vibration, it is transferring the heat from this molecule to this molecule. Then like that all molecules will start vibrate, then from one molecule to another molecule the heat will transport from this end to this end. So this is called the conduction mode of heat transfer. This is how the heat is transferring through conduction. Heat is not only transferring, conduction not only happening in the solids but also happening in the liquids and gases also. So in liquids also, suppose if we take, this is a one pan, in this pan I am filled with water. So in suppose considering the solid and liquid or gases, in solid molecules are closely packed, but in liquids molecules are not closely packed, and also molecules are allowed to freely move inside the particular object where we filled. So the what will happen here, just opposite to this, when I heat this water, what will happen, these molecules will start move. Suppose the molecules at the bottom level, when I heat, the density of the molecules will come down, so that the low density molecules will move up and it will go to the top surface and it will transfer the heat. So that the molecules is moving and transporting the heat from the bottom region to the top region. So this is also kind of conduction only, so that conduction is not happening only in solid bodies but also it is happening in the liquids. And similarly in gases also, molecules will, suppose if we take any plate which is at some degree temperature 80 degrees Celsius, atmospheric air is coming and it is flowing over this plate. What will happen? This, suppose you take this body temperature as Ts and the atmospheric air temperature as T infinitive, so that there is a temperature difference between the air and the solid object. The solid object is at the temperature of 80 degrees Celsius, atmospheric air let us take 28 degrees Celsius. What will happen? The air will come and flow over this place and this air will extract the heat from this body. So that when it extracts the heat from the body temperature will come down and the air temperature will increase. So what is happening here also, it's a kind of conduction is happening. So conduction not only happening in solid, it also happening in the liquids and also in the gases. So this is how the conduction mode of heat transfer is happening. Convection is nothing but, so for this conduction there is one governing law. So the governing law for the conduction is Fourier law of heat conduction. Fourier law of heat conduction is important equation, so that I will write the equation. So that is Fourier law heat conduction equation, which is given Q equal to minus K A dt by Tx. So this is the Fourier law of heat conduction equation. It is very important equation where Q is nothing but heat transfer. Q is amount of heat transfer, like A is cross sectional area of the body, area of the object, you can say any object you can take, where dt is the temperature difference, dx is the distance travelled by the heat, distance travelled by heat. So this is the Fourier law of heat conduction equation. So in this equation, which is given Q is equal to minus Ka dt by dx, for example, if we take any plane body like this, let us take, this is one wall, this surface of the wall which is at the temperature T1 and this end surface of the wall which is at the temperature of T2. So heat will always travel from high temperature to low temperature. This is a kind of linear transformation of heat. So what is happening? Suppose this wall is made of one material, maybe you take as a copper or any object which is made of copper, so that, and the area. So heat always will flow normal to the area. The direction of heat always will be normal to the cross sectional area of the object. Suppose heat is traveling, so you see this, the heat is always perpendicular to the cross section area. So Q is directly proportional to area. And also temperature difference you see. So that temperature difference, you can say heat is always flowing from higher temperature to lower temperature. So that is a negative gradient. So dt is nothing but T1 minus or T2 minus T1, Tt or T2 minus T1, and the distance travelled by the heat. So from where to where it is travelling, that is the thickness of the object which you take as a L. So dt by T or T2 minus T1 by L. So this is the actual heat conduction equation. Q is equal to A into delta T by L, delta T or dt, which is equal to the temperature difference between the two planes or two walls of the given object, that is Q is equal to, or simply I can write Q is equal to A into delta T by L. Then this negative sign why I am putting, so if we see that the temperature is gradually decreasing, so heat is transferring from higher region to lower region. So to indicate that only negative sign we are putting, that is Q is equal to minus A into delta T by L, that is proportional, directly proportional to area and temperature difference between the two plane walls, and it is inversely proportional to the length. If we increase the length, then the heat transfer will decrease. Then there is one constant proportionality which is K, that is minus K into A into delta T by L. So what is this K? K is nothing but thermal conductivity of the material. So that is the constant value, which is the property of the material. Each and every material has its own property. So that for better heat transfer we can choose higher thermal conductivity material. If we choose copper, then there will be some high heat transfer. So if we want to transfer heat more, then we can choose high thermal conductivity material. So that if you don't want to transfer the heat, or you want to protect the heat, you want to protect the loss of heat, then we have to choose the less thermal conductivity material, or also a kind of insulator, so that you can protect the heat. That is you can do some isolation, so or you can do some insulation. So this K value is nothing but thermal conductivity of the material. So this is the governing equation for conduction, which is Q is equal to minus Ka into dt by dx, where K is the thermal conductivity of the material, that is constant value, that will vary with respect to the material, and A is the cross sectional area of the object, delta T is the temperature difference between the two planes of the wall, and also dx is, or L is nothing but how much amount of how much distance the traveled by the heat is nothing but dx or L. So this is the Fourier law of heat conduction equation. Next topic is convection. So what is convection? Second mode of heat transfer is convection. Convection, what is convection? Convection is also a kind of mode of heat transfer in which the heat will transfer. There will be one medium, at least one medium should be either fluid or gas. Suppose if I take a tea cup, okay, this is a cup in which I filled the tea or coffee, which is initially at some 40 degrees Celsius at room temperature. Now what I am going to do, this tea cup I am going to place in the open room. Okay, so now I am placing this in open room. So in open room, so suppose this surface of the cup, which is initially at 40 degrees Celsius, now I am placing this tea cup in the open room. When I place this tea cup in the open room, what will happen? In the open room there is some atmospheric air which will come and flow over this surface of the cup. Though that surface air temperature will be definitely lesser than this, because atmospheric temperature is like 28 to 30, maximum 30. It will be between 28 to 30 degree. Definitely this air temperature is lesser than the surface temperature of the tea cup. What will happen? This fluid or air which will come in contact with the surface of the tea cup, and it will extract the heat from the surface of the tea cup, so that after some time we can feel that coldness on the surface of the tea cup, so that this will cool down because of convection. Convection is nothing but the heat transfer between the solid medium and the fluid medium. There will be at least one fluid medium for the heat transfer to take place. So that is, the medium is, at least one medium should be fluid and another medium should be solid. So this is called convection. And for convection there is one governing law, which is Newton's law of cooling. This is the governing law for convection, Newton's law of cooling. So here heat transfer, Q convection equal to H into A into Ts minus T infinitive. This is the Newton's law of cooling, or governing equation for convection. Here one new parameter which is called H. H is nothing but H is heat transfer coefficient. Heat transfer coefficient. The unit for the H is watt per meter square Kelvin. Okay. So this is also a constant value that will vary with respect to the temperature of the surrounding. So if the surrounding temperature is less, then H value will be less. If the surrounding temperature is high, then the H value should be high. So that H value will vary with respect to the ambient temperature, which is nothing but heat transfer coefficient. The unit for H is watts per meter square Kelvin. And in convection there are two modes of convection, or two types of convection. One is natural convection natural convection or free convection. Natural convection are also called as free convection. Second one is forced convection. There are two types of convection. One is natural convection or free convection, another one is forced convection. So natural convection or free convection is nothing but is just kind of heat transfer takes place without any external aids. Like suppose as I said already, I am having one teacup that I am keeping in the atmosphere, so that atmospheric air is coming naturally and which is flowing over the surface of the teacup and which is extracting the heat from that teacup. That is called a natural convection. But if I go for a forced convection, then in forced convection mode of heat transfer, what I will do, instead of I am just naturally supplying the air to the solid body, I will use a fan or pump. So that what I will do, suppose if I take an object on which if I keep in the open room, then atmospheric air will come and flow over this. Suppose instead of doing like this, if I use a fan, what the fan will do? The fan will force the air to flow over the body. So when the fan forces the air to flow over the body, the velocity of the air will be high. When the velocity of the air will be high, that will extract more amount of heat, so that I can improvise the heat transfer rate if I use forced convection. So forced convection mode of heat transfer is better than natural convection, but cost wise this is has some drawbacks. So we have to spend some cost, like for fan or for pump we need to spend some cost, but for natural convection we no need to spend any cost. So forced convection is not a cost effective method, and also there should be some space constraint. Suppose if I want to cool, like if we take laptop or mobile phone, for cooling application we need fan, so that suppose if we use laptop for more time, so that all the ICs like integrated circuits inside the laptop will heat it up, so that we need to cool the integrated circuit. So in the laptop, if we see inside, there is one fan. So that fan is what it is doing, it is just circulating the air to flow over the motherboard of the laptop, so that air is forced to flow over the motherboard, so that it is extracting more heat. So for that we need space constraint and also some kind of cost that we need to spend, suppose if we choose for forced convection. So this is called convection. Next one is radiation. So the another mode of heat transfer, that is the third one, is radiation. So radiation mode of heat transfer is completely different from conduction and convection. For conduction we need one medium which is solid, for convection we need one medium which is fluid. For radiation it doesn't require any medium, it doesn't require any medium to transfer the heat. So how then it is happening? Through electromagnetic waves. Through electromagnetic waves, heat is transferred from one place to another place. So that here we no need to use any medium, like heat will automatically transport through some electromagnetic waves from one place to another place. Best example is sun. So from sun is the electromagnetic waves are reaching the earth without any medium. So it doesn't require any fluid, it doesn't require any solid. So that automatically the heat is transferring through electromagnetic waves from the sun to the earth. So sun is the best example for radiation. If in radiation there is one concept, suppose if we take one body which is a solid body, suppose in this body some radiation is coming. Okay, so this is incident radiation which is falling on the body. That after that, how much amount of incident radiation which fell in the body, some amount of radiation will be emitted, that is called emissivity, and some amount of radiation will be absorbed by the body, some amount of radiation will be reflected from the body. So this is a concept of radiation. So for governing law to the radiation is, so that this we have to remember, this is absorption, this is reflection, and this is emission. How much amount of radiation or heat energy which is falling on any body. In radiation there will be three things, one is emission, one is absorption, and another one is reflection. Suppose if the body is glass, then that will reflect more amount of heat. Suppose if the body is black body, then that will that will emit all amount of radiation. Like it is depends on what type of body it is. If it is a grey body, then that is different. Okay, so this is called radiation. So the governing law for radiation is Stephen-Boltzmann law, which is governing law for radiation. Boltzmann law, which is, that is Q due to radiation is equal to sigma into epsilon into delta T the whole power 4, which is Ts power 4 minus T to T infinity power 4. So where sigma is Stephen-Boltzmann constant. This is Stephen-Boltzmann constant. The value for that is 5.678 into 10 to the power of minus 8 watts per meter square Kelvin power 4. So this is the constant value which we need to remember when we going to work out some numerical problems in the radiation equation, which is this value is found by some experimental thing, so that we no need to discuss in deep. So this value we should remember, that is sigma, which is equal to 5.678 into 10 to the power of minus 8 watts per meter square Kelvin power 4 is the unit for Stephen-Boltzmann constant. Here epsilon is emissivity. Epsilon is emissivity. That emissivity will vary with respect to the type of body. So and also it depends on due to the roughness of the body. So that if the body is smooth or very polished body, then there will not be more emission. So that body will absorb more amount of heat. So that emission is very less if the body is very polished, like kind of metal body. So if the body is rough, so then there will be some emission. So that emission will be like if we take any black body or the roughness is high, then it will be 0.9 or 0.8 to 0.92 you can say. That will be 0.8 to 0.92 the emissivity of the body. For high emission, the body should have some roughness. Due to roughness only it will emit some amount of radiation. That is, from irradiation it will emit some amount of radiation which should be in the range of 0.8 to 0.92. And this Ts is nothing but surface temperature of the body. Means what body we are considering, that body surface temperature is Ts. T infinity is, suppose this is the body. In this body, this is the Ts. Ts is nothing but temperature of the body, and the body, suppose I am keeping inside one room. Okay, so that room temperature is T infinity, always fluid temperature. So in the room what will be available? Air only will be present. So the temperature of the air or temperature of any fluid we are denoting in heat transfer as T infinity. So T to the power of 4, Ts to the power of 4 minus T infinity to the power of 4. Okay, so what is Stephen-Boltzmann law? The rate of emissive power, that is the rate of emissive power which is directly proportional to the fourth power of its temperature. That is the Stephen-Boltzmann law. So he used that after completion of some experiments, he found that value sigma, which is equal to 5.674 into 10 to the power of minus 8 watts per meter square Kelvin power 4. So this is radiation. Okay, so now we have seen three modes of heat transfer. One is conduction, another one is convection, and the another one is radiation. Okay, so these are the modes of heat transfer which we have seen in the first lecture. So that is the first topic which is given in the syllabus. So that one is modes of heat transfer. So modes of heat transfer: conduction, convection and radiation, and all the governing equations for this all modes of heat transfer also we have seen. Problematic parts we will see at the last. First we will cover the syllabus like the theory topics. Later we will go and solve the numerical problems on each and every topic. Some basic numericals only, not very big numericals will come to your examination. So next one is one dimensional heat conduction equation. Okay, so we have to see some derivations for this one dimensional heat conduction equation so that you can remember the formula. Instead of just writing the formula, I want to explain you clearly about how it is one dimensional heat conduction equation for plane wall, how the heat will be conducted, and for suppose if the object is cylindrical object, so in cylindrical object how the heat will transfer. Suppose if the object is spherical or sphere kind of ball kind of things, suppose if the object is sphere or ball, in which how the heat will transfer. So that these three things we will discuss in one dimensional heat conduction equation. What is the one dimensional heat conduction equation for plane wall, what is the one dimensional heat conduction equation for cylinder, and what is the one dimensional heat conduction equation for sphere. These three things we need to study in one dimensional heat conduction equation. So we will see one by one. So the second topic in the syllabus is one dimensional heat conduction